So up to this point, we've talked a lot about measuring something in moles. What we're going to be actually able to do now is measure our concentration of our solution in moles as well. This is referred to as molarity. Molarity is represented by a capital M. It is really important that you use a capital M here because there is something that we're going to be using as a lowercase m. But what this is, it represents the moles of solute dissolved in each liter of solution. So molarity, or capital M, is equal to moles over liters. So it's moles of solute over liters of solution. Okay, so let's take a look at an example problem. So we're going to calculate the molarity of a solution formed by mixing 10 grams of sulfuric acid with enough water to make a 100 milliliter solution. So the first thing we have to do is calculate the moles of sulfuric acid. So sulfuric acid, if you didn't remember, is H2SO4. So for our conversion, what we're going to do, we're going to convert it from grams to moles of sulfuric acid. We calculated the molar mass of the sulfuric acid from the periodic table. Moles will continue to be used for the rest of the year. So it's an important thing to know. So we're going to plug this into our calculator. So you should get 0.102 moles of sulfuric acid right here. Okay. So then we have to calculate liters. Quite often when we are looking at a unit, we are measuring something in milliliters because that's practical for us to measure in. However, for this molarity, it has to be in liters. So we have to convert 100 milliliters to liters. So 1 liter has 1,000 milliliters in it. So we're going to end up with 0.1000 liters. The tricky part here is you want to make sure you're keeping your same quantity of sig figs. So we had 4 sig figs here, so we should have 4 sig figs in our final answer. 3 of which are zeros, which is fine. But the 1 and then the 3 resulting zeros are all considered significant. So now we're able to calculate the molarity. So we're going to have 0.102 moles over 0.1000 liters. Now you would normally plug this into your calculator. It's a pretty easy calculation. So it's going to end up being 1.02 molar. And then just like in moles, you want to make sure you're including what the substance is. So when you have the capital N, you usually say molar, kind of like the tooth, describing what you have. Also notice the way I wrote my M. It's approximately the same size as my numbers. That's how you write a capital M. It's really important that the capital M looks different than your lowercase m. This problem is asking for what is the mass of sodium nitrate needed to produce 500 milliliters of a 0.5 molar solution. So sodium nitrate is NaNO3. In this problem, remember molarity is moles over liters. Molarity we have. And we have the volume. Now we're going to have to convert this from milliliters to liters. This conversion, if you don't want to show your milliliter to liter conversion, that's fine as long as you're doing it correctly. So remember, 500 milliliters, there's 1,000 milliliters in 1 liter. We're dividing it by 1,000, so we're going to end up with 0.5000 liters. We're solving now for moles so that we can figure out the mass of the solution that we want. This is a common calculation when we're in the lab. We want to figure out what the concentration of our solution will be. So we take our molarity, we multiply it by the volume that we have. So molarity times the liters will give us our moles. So in this case, we'll end up with... So So we've ended up with 0.25 moles of sodium nitrate. Now that we have moles of sodium nitrate, though, we have to answer the question. It's asking for mass. So we have to do a quick mole conversion. 1 mole of sodium nitrate to grams. We're going to look on our periodic table to add up 1 sodium, 1 nitrogen, and 3 oxygen. And we should end up with so our molar mass is 85 even grams of sodium nitrate in 1 mole of sodium nitrate. Our calculator will give us 21.25. We need to keep sig figs in mind here. In the first part, we had 2 sig figs times 4 sig figs. So my answer was 2 sig figs. So I still need to keep 2 sig figs for my final answer. So I'm going to need 21 grams of sodium nitrate. So the other unit to keep in mind here is molality. Molality does sound very similar to molarity. This is a lowercase m. You want to keep that in mind. Usually when I draw molality, I use a script m to make it look a bit different. You also want to keep the size of your m in mind. You want it to be approximately half the size of your number. So a capital M versus a lowercase m, we want to make sure they look different, because on the test, these mean 2 different things. Now, I have had students in the past actually draw a little arrow and say big M or capital M, which is fine if you want extra clarity, but if I can't tell the capital from your lowercase, I can't give you credit for the right value. So again, this is used in industrial processes mostly. So in this example, we're making a seawater solution. The first thing we have to do is we have to take the grams of our solute, which in this case is sodium chloride, and go from grams to moles, which the molar mass from the periodic table is 58.44 grams. Oops, and I flipped it. You don't want to do that. You want grams on the bottom so the units cancel out, and moles on the top. So we'll end up with, you end up with 0.117 moles of sodium chloride. Now, in this problem, it's not real clear what to do. Something to keep in mind is the density of water is 1 gram per milliliter. So you can use that with the volume, if they give you the volume, to get to grams. However, they did give you 24.3 grams, which makes the problem a little bit easier. So there's 1,000 grams in 1 kilogram. So you're dividing it by 1,000, so you'll end up with 0.0243 kilograms. The last step is taking your 2 values and putting them together. To get our molality. So we end up with 4.81 molal sodium chloride. So again, this is a lowercase m. It's about half the size of the number. It's very clear that it's lowercase. The last math we're going to talk about today is a dilution. So some things can only come in a very concentrated solution that we keep in a locked cabinet. So if you have a very concentrated solution, you're able to dilute it by adding more water to it. It's a relatively easy process to do that. The thing that you can't do is, if you have a dilute solution, remove water from it. You can evaporate it, but some of the substances are actually gases. So if you heat it, you're going to remove some of your substance as well. So it doesn't always work out. So that's why sometimes we have a dilution. It's very similar to our gas laws, except instead of pressure or temperature, we're just dealing with M, which stands for molarity. So we have a 12 molar stock solution of hydrochloric acid. We want to make a 250 milliliter solution of a 0.10 molar concentration. So this value would be my stock solution. It doesn't really matter which one you make, M1 and M2, as long as you're keeping them together. So in this problem, we're trying to figure out the volume of the stock solution needed to make a 0.1 molar solution, which is M2, and 250, which is V2. So we need to rearrange this in this case to solve for V1. Did you catch that? This kilogram value is incorrect. It should be this number right here. So 0.0243, which is going to change our answer. You want to make, which will give you the same answer. We calculated it right. I just wrote the wrong thing. Sorry about that. Okay, so we're going to back to our dilution problem. We're going to rearrange this to solve for V1. So V1 is going to equal M2 V2 over M1. Now, you might be thinking, well, this is in milliliters. Do I have to change it to liters for this to work out? The answer is no. As long as your units are canceling out, you can leave them in the units that you have. So we're going to take M2, so 0.10 molar, times V2, which is 250 milliliters, divided by 12.0 molar. Now, before you plug this into your calculator, you do kind of want to think about this. Generally, if you calculated this right, the volume that you get should be pretty small, or at least at minimum smaller than the volume you're trying to make. So that's a common mistake, to flip it, and then you end up with more than the solution that you have, which is a problem. So we're going to plug this into our calculator. So you end up with 2.083 with a capital M here. You want to keep sig figs in mind because the 0.1 has two significant figures. It's going to be 2.1. Oh, it should be milliliters, not molarity here. That's a common mistake, just to put a unit with it. Sorry about that. So you would need 2.1 milliliters in order to make this solution. Now, when you go about making a solution, you always add the acid to the water. So to make this solution, you would add about 245, I would do if it were me. 245 milliliters of just water, add my acid. You always add acid to water because this avoids splashing of the acid on you. It's a safety precaution. So if a question ever asks you what's the other component of the solution, it's water in order to dilute it.